Hello everyone, I'm Hao Guo from Tsinghua University. I'm presenting this work on behalf of the authors from Peking University and their collaborators. This paper is titled Xerxes, Extensive Exploration of Scalable Hardware Systems with CXL-Based Simulation Framework. First, let's look at the motivation. CXL3 introduces features like port-based routing and device-managed coherence, enabling arbitrary non-tree topologies that go beyond the traditional host-centric hierarchies in CPU memory systems. This is a conflict with traditional research, which assumes a host-centric system. The problem is the simulation void. We don't have CXL 3.0 hardware yet, and the existing simulators aren't good enough to model these new fabric behaviors. Xerxes is designed to fix this. Specifically, there's a big gap between protocol evolution and hardware availability. As you can see on the timeline, CXL3 was defined in 2022, introducing major features like back invalidation and peer-to-peer topologies. However, hardware is lagging. Even in 2024, full CXL3 hardware is still unavailable. Because of this, simulation is the only viable path for research right now. Looking deeper, CXL1 started in 2019 with basic expansion. CXL2 added memory pooling in 2020, but hardware for this has only partially caught up. This lag means researchers must simulate to study advanced features like non-tree topologies and distributed coherence. So, why do existing tools fall short? First, real hardware isn't commercially available at scale, so we cannot test complex rack scale dynamics. Second, traditional simulators typically fall into two categories: computation-centric and network-centric. Computation-centric simulators, such as Gem5 and GPGPU Sim, are built around a host-centric architectural model. They model memory as a strict hierarchy of components tightly coupled to CPU, lacking a flexible interconnect layer capable of modeling a scalable CXL fabric. Network-centric simulators, like BookSim and Garnet, are designed to simulate complex network topologies and routing algorithms, but are fundamentally unaware of memory and coherence semantics, as they model generic packets rather than stateful memory requests. Third, NUMA emulation lacks physical layer fidelity. It cannot model PCIe behaviors like flow control and lane contention. In more detail, these flaws mean that current methods cannot accurately capture protocol interactions, such as distributed nature of CXL coherence, leading to unreliable results to large-scale systems. Xerxes was built to solve these specific challenges. Now, let's move to design of Xerxes. Xerxes is a novel framework. It uses a decoupled architecture and graph-based connectivity to faithfully model CXL3 mechanisms. This design allows for a modular simulation of diverse components, ensuring scalability and accuracy in representing emergent CXL features. Here is the high-level architecture. We separate the system into two layers to make it scalable. The device layer in blue models components like hosts and accelerators as independent components. The interconnect layer in red manages the connections. It uses a graph-based approach to support arbitrary topologies using port-based routing. We also provide extensible interfaces to easily attach existing simulators like DRAM Sim 3. This two-layer approach decouples physical connectivity from device logic, enabling simulation of complex, non-hierarchical fabrics that traditional tools cannot handle. Let's look closer at the device layer. It features like a modular component design, like devices like hosts, expanders, or endpoints are modeled as isolated blocks. This supports plug and play. Users can add new devices without changing the existing code. It is also highly extensible for developers to create custom CXL devices. Devices act as peer-independent components, managing their own state, which aligns with CXL's shift away from host-centric models. Next is the interconnect layer. This layer models the topology as a graph, where devices are nodes and connections are edges. Crucially, it natively supports port-based routing. This allows us to simulate non-tree fabric, which is a key feature of CXL3. Configuration is simple, making it easy to define complex, scalable fabrics. Port-based routing enables flexible forwarding, supporting arbitrary topologies via routing tables, which is essential for rack-scale systems. Now, let's detail the key components. The requester models the computation. It acts as the source of memory request, simulating a CPU or an accelerator. It has two modes, a request generator for synthetic workloads and trace replay for running real-world traces. Internally, it handles queuing, address translation, and caching before requests enter the fabric. This component ensures accurate modeling of memory request origins, including address mapping and the coherence management at the source. For the interconnect, we have the bus and the switch. The bus connects two devices. It models PCIe 5 or 6 links, supporting full duplex bandwidth allocation. The switch supports port-based routing. Each port has configurable bandwidths, and it supports custom routing policies, allowing us to simulate diverse network topologies. These elements capture PCIe-specific behaviors like bidirectional links and adaptive routing, critical for realistic CXL simulation. For coherence, Xerxes implements device-managed coherence. This offloads coherence work from the host to the devices. Xerxes includes an inclusive snoop filter. It tracks who shares the data. If there is a conflict, the device coherence agent issues a back-embedded snoops to peers, collects responses, and grants ownership. DMC enables scalable peer-to-peer communication, reducing host overhead, and the snoop filter's inclusive design tracks shares in device memory modes like HDMDB. Xerxes is also extensible. For example, we integrate it with DRAM Sims 3 for accurate memory simulation. The challenge is synchronizing the clocks. The solution is a clocking event mechanism that syncs the two simulation domains. This integration allows seamless attachment of third-party models without kernel modifications, enhancing simulation fidelity. The next part is simulator validation. We calibrated Xerxes against real hardware to ensure the results are accurate and trustworthy. This step is crucial to validate the framework's predictive capabilities for unreleased features. The calibration platform uses a 4th-generation Intel Xeon processor and a mounted CXL memory expander. We tune simulator parameters like arbitration delays and buffer sizes to match the measurements from this physical hardware. This established a solid ground truth baseline. The methodology involved empirical measurements of latency and bandwidth to align simulation with real CXL behaviors. Here are the validation results. Xerxes shows great fidelity. The idle latency and bandwidth closely match the hardware. The error rate is below 8%, with an average of just 4.3%. Compared to existing emulation methods, which deviate significantly under high load, Xerxes remains accurate. This accuracy holds across diverse workloads and traffic patterns, unlike simpler approaches that fail under contention. Finally, we show design space exploration. Xerxes provides architectural insights for next-generation CXL systems. These explorations uncover key design considerations for scalable hardware. We have several insights. The first insight is about topology. As shown in the charts, tree-like topologies suffer from bottlenecks at the root switch. In contrast, scalable topologies like spine leaf offer linear bandwidth scaling because they provide multiple paths. The takeaway is that scalable topologies are essential for high-performance CXL fabrics. For example, tree topologies lead to head-of-line blocking, while spine leaf distributes load, improving overall system performance in large-scale setups. When simulating large-scale topology, Xerxes is very efficient. It can simulate up to 64 hosts in under 90 seconds, using less than 200 megabytes of memory. This makes it feasible to explore large-scale topologies quickly. The second insight focuses on device-managed coherence. We found that hardware policies matter. For the victim selection policy, LIFO, namely last in, first out, works best. It reduces back invalidations by about 16% by evicting streaming data first. At the protocol level, we found that an invalidated block length of 2 is the optimal sweet spot. Specifically, LIFO is well suited for the cache-miss-heavy patterns in snoop filters, while the block length balances performance benefits against bus contention. This demonstrates how Xerxes uniquely facilitates the co-design of hardware policies and protocol features. The third insight highlights the physical layer. Full duplex transmission boosts bandwidth. With a 1:1 read-write mix, you can approach twice the theoretical bandwidth. However, header overhead is a constraint. Small packets with large headers will diminish this gain. Xerxes accurately models these physical layer details. This phenomenon arises from PCIe's bidirectional links, and mixed workloads maximize utilization, unlike single-type accesses. To summarize, Xerxes is the first open-source simulator for CXL3. It supports topology-aware fabrics and device-managed coherence. It is validated against hardware with an error rate below 8%. The code is available on GitHub. Thank you for your attention. If you have any questions, please contact the original authors. Thank you.